let's talk about internal forces. So internal forces, is it okay if I sit down? It's kind of convenient working off of this and whatever, and you've got these handouts available to you. So in chapter 6, in chapter 5 you did rigid body equilibrium, both 2D and 3D. In chapter 6 you did trusses, frames, and machines. And as you sequence through the class, you've looked at force systems, and then you found resultants of those forces. And then when you got to equilibrium, you found support reactions. You got this beam or this shape that's got loading, and you found the support reactions. In chapter 6, when you did trusses and frames and machines, now you actually, for trusses, you cut members. So when you cut a member and you found that internal force and you said this is tension or compression, that was an internal force. Nobody told you that at the time, but you've already done a basic level of internal forces in looking at trusses. And when you cut that and applied the equations of equilibrium to either a particle, which is a joint, or a larger piece, which is a section, you were finding internal forces. So you already did that with trusses. And then with frames and machines, you had this assembly of this frame or this machine. And typically, you might find a support reaction, but you took that frame apart. And when you disassembled it, then basically you had these reactions that appeared once you took it apart. And nobody told you that at the time, that those forces are internal forces to that assembly, or to that frame, or to that machine. And those internal forces only appeared once you took it apart. So you've already done internal forces. But here now, what we're doing, instead of just looking at pins, reactions that we've taken apart, now we're actually cutting members at an arbitrary place within a member. And there are actually internal forces. In any typical member that you cut, there's internal forces at that cut, okay? Because if you've got loading on a particular member, and like if you have a 2-force member, nobody ever talks about this either, but if you basically have a simple beam that's hanging out here with a load hanging from it, let's say this is 100 pounds, and we've got a pin here and another pin down here. You could put a straight 2-force member on this guy, where you've got a single force acting along this member. But what if you have an L-shaped 2-force member? Something like this. So this is A, B, C, and then D. So if you take this L shape, I'm not going to put dimensions on this, is fine, but let's say this force that's developed between pins B and C, let's say this guy's 60 pounds, just to keep this beam in equilibrium. So the force exerted by this L-shaped member up on this beam is 60 pounds. But if you draw the free body diagram of this L-shaped guy, it looks like this. And then you've got the 60 pounds here, which is the pin reaction of this beam onto this L-shaped member. And if you say, well, what's the internal forces here? If you cut that there and draw this free body diagram, with this force 60 pounds acting on it, there's going to be a shear, there's going to be an axial, and there's going to be a bending moment at that cut, okay? That's one of the disadvantages of using an L-shaped 2-force member. If we would have put a straight 2-force member here, then it's just in compression or in tension, and the only internal force in this guy is just an axial force. There's no shear, there's no bending moment. So there's no tendency of this guy to bend. Now he might buckle. If that load is large enough, he could buckle, but there's not the bending case. But an L-shaped guy, you can but with this off-centered force, you can end up with axial, shear, and bending. And so you have to design this L-shaped member appropriately to manage, to manage it bending and shear. Okay. So basically, a member like this L-shaped guy develops internal forces. So one of the rules, so when you did a frame or a machine or a truss, the whole object is in static equilibrium. So every piece has to be in static equilibrium. So when you isolate a joint, or if you isolate a section, or any piece of that truss, it has to be in static equilibrium. So if we take this L-shaped member here and cut him here, if he's in static equilibrium, which he will be, so whatever, this is 60 and this is 60. So the whole thing is in static equilibrium. But if we cut him here, these internal forces have to be such that this section of this guy is in static equilibrium. So these guys are the equal and opposite of him and have the appropriate bending moment to keep this guy in static equilibrium. So every piece of every member has to be in static equilibrium. Okay? So that's what we're doing with the internal forces. Does that make sense? Is this too basic or is this okay?
That's good.
Yeah. So I'm going to skip over this 3D piece here. Because the 3D typically is not on your exams, but you can appreciate the fact this is like a large cantilevered billboard that you see by the edge of the highway. Huge round post that can be 150 feet tall. You got this huge billboard on this thing. And so you got the weight of that sign and you got a huge distributed load due to the wind pressure on that sign. And so tremendous amount of weight, force of wind. And so in the general 3D case, you can actually have two directions of shear. You can have an axial, and then you have two directions of bending moments about two different axes, and then you can have a torsion about the shaft. So ultimately, in the full-blown 3D case, you can have three forces and two bending moments, and then one torsion. When you get to mechanics materials, you'll deal with what are called combined loading cases where you have stresses due to all of these guys. But I'm not going to work, I think there's one of these in the practice folder, but we don't typically put a 3D problem on the test. So for now, I'm skipping it. So keep in mind, this is an exam review. If I was teaching a section just on internal forces, I would probably spend more time on theory and some of this stuff, but I'm focusing on stuff that you need for the exam. Beam, we already talked about the sign convention for a beam. So let's come back to some examples. So most people are fairly familiar with a beam. If you got a beam and you cut the beam, you've got a shear, a bending moment, and an axial, and that's relatively straightforward. But our exams, we typically put a problem that's not oriented that way. In this case, in this towing hitch, you've got a force applied. The axis of the beam actually goes this way, but the force is applied off of that axis. Down here is another example. And these are examples I've used over the years that are like problems that we've put on tests. Here's another problem where you basically have a beam or a member at an angle, okay? And another case is basically a beam or a member that's vertical or whatever. And one of the things that trips up students is, what direction is a positive shear? What direction is a positive axial? What direction is a positive bending moment? And the short answer to that question is, the tests usually just ask you for the magnitude. They don't ask you for the sign on those guys. So don't worry about the direction. All you're doing is finding the magnitude of these guys. So how do we do that? So if you just take this hitch here, this hitch problem. So you basically have this 400-pound force at a 35-degree angle, and it's 2 inches below this ball, the center of this ball, is 2 inches below the center line of this axis, and then it's 12 inches from here, from the center of the ball to this cut. And so you just cut this guy, And so you actually have two different, for the general internal force problem, you've got two choices. I can actually draw the free body diagram of this guy and then find these forces on the right face from equilibrium equations. But that's actually kind of painful and it's longer. It's easier to just move this force to this cut. And the forces can just be moved directly, but then you have to find the moment of that original force about that cut. And so it's really a resultant problem. And so the resultant of this force at this cut is the equal and opposite of the equilibrium reaction. If you took this right-hand side and found the equilibrium reactions on the right-hand piece, those guys are the equal and opposite of the resultant of the left-hand piece. But it's easier to do the resultant than it is to do the equilibrium. So do the easy part, okay? Make it easy. So basically what we're gonna do is resolve this into two pieces. So I have a 400 cosine 35, which is 327.7. And then I have a 400 sine 35, which is 229.4. And that's applied to a point, which is 12 inches over and 2 inches down. So what is the resultant of this force system on this cut? Well, the forces I can just move directly. And so the 229.4 just gets moved there. The 327.7 gets moved, but I need to preserve the moment of these guys. So the moment of these two forces about this cut, if we take counterclockwise to be positive, I've got 229.4 times 12. If you slide this guy along his line of action, his moment arm back to the center of this cut is 2. And so I have 400 sine 35 times 12 plus this guy times 2. And I get 3.4, basically 3410, or 3.41 times 10 to the third pound-inch here. And so basically, so this force about this cut produces an axial force, which is this guy. An axial force, which is this guy, 327.7. A shear, which is this guy. And a bending moment, which is this guy. Notice my shear is pointed upward. I mean, technically positive shear is down. And so if I really asked you for the sign, this actually would be a negative V. But again, they typically just ask for the magnitude, okay? And so this is like a standard problem with the horizontal member. Does that make sense? But sometimes we'll do it at weird angles. And so what if you've got this member, this part of a frame or part of this assembly or whatever, and you happen to know it's basically this guy is, 40 degrees from horizontal. There's a horizontal 600 Newton force acting up here at 40 degrees to the member. And the problem says, what are the internal forces at this section AA, which is 0.8 meters from where this force is applied? And most students get really confused at that, but just breathe and relax, okay, and think about this. So keep in mind, when we're talking about axial, shear, and bending moment, what we're really doing is we're looking for forces that are in a coordinate system that's basically, you've got an X prime system and a Y prime system that exists at the cut. So whatever cut you make, I'm interested in a force that's perpendicular to that cut. We call that X prime. We're looking for a force that acts along the cut. That's a Y prime. And then we're looking for a bending moment. You basically are about that point. So think in terms of a coordinate system. And so what I want to do is, since I know the angle between this applied force and my member, and really my X prime axis is going to be aligned along that member, so I'm just going to resolve this 600 Newton into a component along the member and a component perpendicular to the member. And so I have 600 cosine 40, which is 459.6, which is this guy. And then a 600 sine 40, which is this guy, which is 385.7. And so instantly then, this becomes my axial, and it's in compression. This becomes my shear, once I move them down here. So I have an axial, which is in compression, a shear, which acts this way. And then my bending moment is just the moment of these components about that guy. So the line of action of the 459.6 goes through that point, so its moment is 0. But this guy is 385.7, and his moment arm is 0.8. And so that gives you 308.6 Newton meters for your bending moment here. So don't be intimidated by these things being drawn at weird angles, okay? You're just resolving your forces into components along the member. And don't worry about the sign convention. If you actually go to that practice exam, this is the practice exam. And so again, on the typical exam, they've got one problem that there's 3 questions. So this is we'll look at this guy here in a moment. This is a weird question. The angle is really weird. But the first question based on it is the magnitude of the shear force, not a sign, just a magnitude. The second is the magnitude of the normal. And the third is the magnitude of the bending moment. They're just magnitudes, so don't worry about signs. Just magnitudes. One more example I'm going to show you is a T-shaped. Just all different orientations of things, T-shaped. So this is off an old problem, old final too. So you've got a T here with a weight 100 Newton, and then you've got a 147 Newton force here and here. And so we can take this, these are coming off of 2 sides of a pulley. And I don't know if you remember, when you draw this free body diagram of a frame, and there's a cable coming from off the frame around a pulley and then back away, if the process of cutting the free body diagram, you cut both of those cables, you can concentrate them at the pin. And so I can take this 147 sine 42, which is a 98.4, which is this way. I can take 147 cosine 42, which is 109.2, which is here. These are the 2 components of this guy. And then you have the 147 that's also here. And you can put them both at the pin, which is what we did. And then you have this 100 Newton here. And so this is what the picture looks like. But now you've got a vertical cut. You've got a cut on a vertical member. And so, again, the direction is not important. If you look at the shear, the only shear force is the 98.4. And so the shear is 98.4. The axial is 100 plus 147 plus 109, which is 356.2, is the axial. And then the bending moment is the moment of the 100 times 2, the 98.4 times 2.65, and then this guy plus this guy times his moment, which is 3. And so that's the moment there. A little more complicated, but you get the bending moment. So, questions on that? Those are internal force problems.